Welcome again. Today we're gonna have the second part of the problem solving session, and today we're gonna cover a couple more examples related to the horizontal alignments. Last time we covered the vertical alignments, and today let's go and again do a couple examples for the horizontal alignments. It's gonna help you for the homework as well as for the exam. Let me share the screen. Okay, so you should be able to see. Can everyone see the textbook that I'm sharing?
Yes.
All right. So this is one of two examples that I want to share with you today, and we are gonna go ahead and calculate it ourselves and see if we can get it right. So the first example is example 3.14, and it has to do with the super elevation horizontal curve. So the question says, and maybe for the better, instead of just looking at the answer, we can just have a screenshot of it without looking at the solution. And I can stop the share. And I'm gonna come back to the sharing the note. Okay, so here's the example. It's a horizontal alignment and instead of a vertical alignment. So the roadway is being designed. Roadway again is being designed for a speed limit of 70 miles per hour. So the speed V is 70 miles per hour. At one horizontal curve, it is known that the super elevation is 8%. So that's the small e. If you recall again, the super elevation we call it as e, and that is 8%. That is 8%. And the coefficient of side friction is 0.1. The side friction is 0.1. Determine the minimum radius of the curve. So we need now to get the r, or what we call the RV. So how can we get the r? So if you recall from last lecture or a couple lectures ago when we derived the equations for the minimum radius, it's the speed square over g times fs, that is fs, the side friction, plus e over 100. So that's a straightforward question. We're gonna get to learn how to do it from the equation, or we can pick it up from the table that's in your textbook with some correction that I found that needed to be on that table. So the RV, the minimum radius, then the minimum radius for that horizontal curve is v squared, which is 70 miles per hour. A common mistake here that I hope everyone would not do in an exam or homework. These equations are always based off feet and seconds, because at the end the radius it's in feet. There is no radius in miles. So the radius is in feet. So please 70 always multiply it by there is a factor again 1.467, and that is actually a conversion from the miles per hour till feet per second, and that is squared. Where did we get this 1.467? It's really again the 70 miles per hour. Again, we really multiply this by again 5280 over 3600. That's basically where this number is. If you divide 5280 over 3600, you're gonna come up with 1.467. So this is just a conversion factor in order to get it into feet per second. Any question on that? Very crucial, very important to get that right. So that's the speed squared over g, and that is 32.2, that's the gravitational coefficient, times fs, which is 0.1, and that is unitless, plus e over 100. E is 8 over 100, so that's 0.08. And therefore, the minimum radius for that horizontal curve is 1819.4 feet. That is, again, that's the minimum the minimum radius to have in order to handle this speed, 70 miles per hour, and a super elevation of 8% and the side friction of zero point 0.1. Straightforward, but again, sometimes this is a common FE question, by the way. So keep that in mind. It's a simple question, yet you need to be aware of the equation as well as the speed here is 70 miles per hour that need to be changed to 1.467. So that's the number. If you again, some engineers instead of doing it by hand, you can go to the table that we also explained last time. So let me stop the share here quickly and share the textbook, and let me point out that to you where we can find this table. All right. So here, let's go down. First, check. Let's check again what we did is right. Again, the RV is RV again, V square over G times Fs plus E over 2. So 70 miles per hour times 1.467 over 32.2 times 0.1 plus 0.08. So that's 1819.4. Or let's go to the table. I showed you this table, and please go back and review your notes. You're going to find again the table 3.5. This is defines for you the minimum radius using limiting values of E and Fs. So for the first, like for the first part of this table, for example, I have here design speed from 10 to 60 and the maximum E from 4, this is 4%, and the Fs from 0.38 to 0.12. But for our case, we know that the speed was 70. We know that the E is 8. So this is the line here. 70, that's 70 miles per hour, and the super elevation is 8%, and the side friction is 0.1. So by doing going through the equation, again, it's about 1814.08. That's just again an approximation, or again based on the calculated R. For some reason, again, it's a little bit off of what we calculated. But what I want to point out to you, the rounding here is not always, again, it's not always correct. For some reason, again, there is a mistake here. For example, whenever you calculate the R, let's say 15.9, and then you're not going to give this to the contractor as 15.9 feet. You always bump it up to the higher number to be more conservative. So that's why if it's 15.9, you're going to report it as 16. If it's 41.7, you're going to report it to the nearest feet, 42. All these numbers were somehow, and sometimes even to the nearest 5 if the number is big, like this is here 1186, again 1190. For some reason the bottom part here is not done right, where actually at least for this one here, this is 1814.8. This is supposed to be 1820, not 1810. So please make sure, again, this is supposed to be 1820, not 1810. But that's your first example. Any question on this example? All right. So let me go now to the next question. The horizontal curves are typically easier than the vertical curves in nature. But let's go through another example here that can help you for your homework number 3. So we finished the example 3.14. We're going to do now example 3.15. All right, so this is the stationing on horizontal curve, and how can we get all the factors that we've talked about last time. So example 3.15, let's take again a screenshot of that and solve it ourselves. All right, example 3.15, we're saying it's another horizontal curve is designed with a 2000 feet radius. So now, instead of, this is the first example, 3.14 was a design problem where I have the speed limit, I have the super elevation, I need to design the radius of the curve. This is now an analysis problem where the radius is known, which is, again, this is the 2000 feet radius. The curve has a tangent of 400 feet, and the pi at station 103 plus 00 determine the stationing of the pt. So this is the analysis problem. So now we need actually to draw that the curve, and trying to understand again all the what we've done before. So this is here the curve. Well, let me undo that and draw it a little bit. So here's the curve, and I have, this is here the r, the radius, and this is the PC, and this is the PT. And really now if I want to draw the tangents to meet at the PI, and the tangent here, this is the T. This is again a little revision for your exam coming up. And the length along the curvature, that's the L. That's the L. And then I also have, this is the delta. And then I have, if I want to draw a horizontal line here, this distance here is, we call it M, the middle ordinate, and the E. And E is the external distance. So now what I was given in this problem is I have the T. The T is 400 feet. This is the tangent length, 400. So that is here. So T is 400. And the designed length, radius, the R, is equal to 2000 feet. And the station of the PI, this one right here, is 103 plus 00. We need to get the station of the PT. All right. So that's what actually what we're planning here, what we need to do. In order to do that, as you can tell, we do not know the length of the curve, neither the delta, because really what we need to do, the plan here is, I need to, from the PI, I need to go back and get the station of the PC, and from the station of the PC, since this is horizontal curve stationing is measured along the alignment of the road, then the PC stationing, once I know the station of the PC, I'm gonna add it to the L to get the PT. So really the plan here is we need to get the station of PC, and then once we get that, we're gonna add the station of the PC plus L to get us the station of PT. So how can I get the L? That the length, the length of the curve itself. We know the radius, but I do not know the L. If you recall from last time also, I gave you all the equations, which again, they're gonna be provided in your exam, by the way. The first equation that we talked about last time was the tangent is equal to the radius of the curve times tangent of delta over 2. Because I really need to get delta and I need to get L. Why is that? If you remember also the L, the equation of the L was pi over 180 times R times delta. So in order for me to get the L, I need to know the R, the radius of the curve, and I need to get the delta, the angle. So, and if I start with this equation, I have two unknowns, the length of the curve and the delta. and I cannot do that. That's why I'm starting with the other equation. The tangent, the tangent length is equal to the radius times tangent of delta over 2. The t is known and the r is known. That's why I can get the alpha, the delta. So let's go here and say, okay, the t, that is equal to 400. That is equal to the radius, which is 2000 feet, that was given to me, times tangent of delta over 2. If I divide each side by 2000, that means now 400 over 2000. That's going to be equal to the tangent of delta over 2. Therefore, really now to get the alpha over 2, this is here another common mistake. Whenever you're going to do now the tangent, the inverse of the tangent, you're going to get the value of alpha over 2. So now what you can do, you can say, okay, tangent inverse of the 400 over 2000, that's equal to the delta over 2. So when you do it, you're using your calculator to get the tangent inverse of 400 over 2000, you are going to end up with, well, why didn't you do it? While, again, let me do it here myself. So tangent inverse of 400 over 2000. Another thing, by the way, I need you to make sure that your calculators, there is little d at the bottom of that calculator in degree, not in radians. Please make sure that your calculator is using degrees, not radians. Otherwise, again, you're going to end up with weird numbers. So 400 over 2000, then tangent inverse of that, you are going to end up with about 45. So when you do that, value here is going to give you 45 point, roughly 0.24 degrees. A common mistake that you're going to go ahead and report, you know what, delta is equal to 45 over 2, 45.24. That is not the case. 45.24, that's equal to delta. No, actually, no, I'll take that back. Actually, no, if you do the tangent alpha, that's going to be, can someone check that from your side, please?
I got 11.31.
Yes, I was about, yeah.
Me too.
Me too.
Good. I'm testing. So it's 11. That's actually 11.31. Good. So 11.31, most of the time, or not most of the time, let me take that back. Half of the students will say, okay, alpha, I mean, delta is equal to 11.31. But that's actually the value of alpha over delta over 2. So delta itself is equal to 22.62 degrees. So once I get that, now I can go back to the previous equation, this one right here, and that's going to be the to get the value of the L. So L now is going to be equal to pi over 180 times R times delta. So that's equal to pi over 180 times the radius, which is 2000 feet, times delta. Here is going to be again 22.62. That will give me a length of the curve. The length of the curve is 789.58 feet. That's the length of the curve. We're not done yet. Sometimes you reach at a certain stage and you question yourself, what am I supposed to get at the end? This is not the end result yet. This is the length of the curve. Once you get the length of the curve, now we're gonna go back to plan here. This is, please write this down. This is the rule of thumb here when we do the stationing. So if you know the station of the PI, we need from the PI, we're gonna subtract the T to go to the PC. And from the PC, again, since the horizontal curve stationing is measured along the alignment of the road, we add the L to get the PT. So the station of, so now the station of the PC is going to be equal to 103 plus 00 minus the T. Another thing here that sometimes we miss, when you're going to subtract the t, what are you going to put here? What's the value of the t?
4 stations.
4 stations, exactly. Good job. So if you put 400, again, the 400 is in feet and the 103 is in stations. They don't talk to each other. So the 400, the t is equal to 400 feet. That has to be equal to, or converted to 4 stations, 4 plus 0, 0 really. That is 4 stations. So 103 plus 0, 0 minus 4 plus 0, 0. That is we're going to end up now with the station of the PC, and that is 99 plus 0, 0. 99 plus 0, 0. Therefore, now the station of the PT is always, we always like to do it from the station of the PC plus the L. The station of the PC is 99 plus 0, 0 plus the L. Same thing. What is the L? We got the L was this much, 789.58 feet. We cannot use it in this equation. What does this equal to?
I think that's 7 stations plus 89.58.
There you go. So it's 7 full stations because every station is 100 feet in the field. 7 plus 89.58. Whoops. So I'm gonna come here and say, okay, so 99 plus 0, 0 plus 89, I'm sorry, plus 7 plus 89.58. So please don't get this wrong here. So the 7 plus the 99. So that's 106 plus 89.58. So that's the station of the PT. Some of you may question why we're doing this. Why not just jump from the station of the PI to the PT? If you do this, you're gonna, the values are gonna be close, but not exactly the same. As I said, and it's mentioned in your textbooks, since the horizontal alignment curve stationing is measured along, again, along that alignment, that's why we like to get the station of the PC, and then we add the full length of the L to get to the PT. That's basically what it is. It's again surveying issue, but if we have, go ahead.
I would say, how would you do it if you were to do PI?
If what?
Would you do half the length?
How would I do it?
If you were to solve it from doing PC to PT, if you were to do a PI to PT, which wouldn't be fully right, how would you even do that?
So the question is, if I have the station of the PI, how would I do it from the PI to the PT?
Yeah, like maybe if you did that, if that was a simple way just to check how close you were to the full answer, if you may just double check your calculations, maybe.
Yes, yeah, but we need to remind ourselves that the really the PI is a point that is not existing in the field. That's why again, stationing wise, yes, you can have a technician standing there, and again to double check the location of the PC and the PT. But really, once we establish the beginning of the curve, which is PC, the importance of the PI become very low from that point of view, because now once we establish the beginning of the curve, now I know what's the super elevation, I know what's the length of the curve. So I would rather to establish that L and add the how many stations from the L plus the PC to get the exact stationing of the PT. That doesn't mean, again, you cannot double check from the PI. So the PI again plus the T is going to give you an estimate, but always again the most accurate answer would be from the PC plus the length of the curve. Does that make sense?
Yes, I just want to see if there was some other way, like to double check my math. But if
Yes.
you can get a PC, you shouldn't even need to. So
yes, exactly. Let's check our work versus the textbook and see again. So here what they did again, almost the same. So the T, we know the tangent, we know the radius. we can get now the delta. The delta again is 22.62 degrees. And then once I get the delta, I can apply the second equation, the length of the curve. I know the pi over 180, and I know the radius is 2000. I know the angle, the delta is 22.62. I get the L, and from the L, again, given that the tangent is 400, the station of the PC equal to the 103 minus the 4 stations. And then again, this is here what I was talking about. Since the horizontal curve stationing is measured along the alignment of the road, which is different than the vertical alignment, so the station of the PT is typically, we like to do it from the station of the PC plus the length of the curve. So that's 99 plus the 7 plus 89.58. This is the length of the curve that we just calculated. And now the station is 106 plus 89.58. So with the horizontal alignment, again, make sure that you really are fully aware of these equations right here. So you need to make sure, again, I'm going to give you the equations, but you need to understand what do I mean by T, what's the PC, what's the PT. So really familiarize yourself with this picture right here and what does it mean. And then the equations are going to be provided, but you need to know what does it really mean. So the D, this is the degree of curve. T, this is the tangent. E, that's again the middle distance. M, the ordinate. L, the length of the curve. So those will be provided. So really, if you know how to run this example, as well as example 3.15 and how to 3.14 and 15, and how to run and use this table right here, that's all, again, what I need from you to know when it comes to the horizontal alignment. Any question?
I have a slightly related question. What chapters are going to be on the test?
The exam will cover chapter 1, 2, and 3. So up to here.
Awesome.
I know again, last Thursday, I posted the lecture for chapter 5. That is not included in your first exam.
Okay, thank you.
You're welcome. Any questions specifically about the horizontal alignment?
Somebody had asked in the chat about what if R is not given?
Oh, and there will be another number. So again, now we're talking about more unknowns than the equations or than the knowns. So it can't be. So if the R is not given, I'll give you the delta. Does that make sense?
Yes, that makes plenty of sense. Thank you.
So yes, if the R, that's a good question, Jose. But again, if the R is not there, then the delta will be there. Or I can give you the E, I can give you the M, and if again going back to where is the textbook one more time? Good question. Let's see here. Where are the equations again? Take a look at this. So I can give you the E. This is very practical question actually. I like it. So E, I can give you the value of the E, and then I'll give you the delta, and then you will be able to get the R. But I just want to make sure that I'm not going to give you more unknowns than what you can handle. That's basically what it is. And in the field, you also will end up having, again, a couple things known, like the T. Most of the time, we know what it is, but if it's not, again, I'll give you the E. But regardless, you will be having enough information to solve the problem. All right. So as I mentioned to the group early on, today again we finished now chapter 3. We finished chapter 5, but it's not included in your first exam. But I would like now to reserve the next again 10-15 minutes or so to discuss the first exam. And instead of waiting, I thought, you know what, if I wait for next week on Tuesday and the exam on Thursday, maybe there is not much time to prepare. So um, for the ones who took classes with me before, typically what I do, I'm gonna go through the slides, all the slides that we've covered for chapter 1, 2, and 3, and I'm just gonna point out, take notes. This is gonna be recorded anyways, but take notes if you want to, and to tell you again what's really more important than the other. Nothing is not important, but I'll try to point out to some of the major things that I want you to concentrate on for the sake of the first exam. Make sense? And please stop me anytime, or if you want to hold your question toward the end, that's fine as well. But this is really informal, just to make sure that you guys are again having expecting what to see in the exam. Really, again, nothing is out of the norm. All right. So let's start with, we started early on. Believe it or not, this is the fourth week of the semester. So we started with chapter one. Let me share that. So this is chapter one. We start with an introduction to transportation engineering system. Basically, the exam, by the way, is gonna include multiple questions. Some of them are conceptual questions, and some of them are mathematical questions. So I'm looking at 2 to 3 or maybe 4 calculations, and those are going to be heavily dependent on chapter 2 and 3, as you may expect. And but that doesn't mean again that's all what I'm having for mathematical equation for chapter 2 and 3. But chapter 1, 2, and 3, I'm gonna pick a couple things, couple questions as conceptual questions, but the calculations are going to be heavily dependent on chapter 2 and chapter 3. So for example, again, things like define the transportation system. That can be something I can ask you about. Define it by your own words, but of course you have to include some of the keywords that I'm asking for. I can ask you what are the two major components of any fixed facility. Sometimes, again, when I say, by the way, briefly mention or briefly explain what's the difference between this and that, I really mean it. So just be brief and to the point. So, for example, if I ask you what are the two major components of transportation network, it's links and nodes, and that's it. I can ask you what do I mean by flow entities, or give me examples. These are passengers or and vehicles. What's ITS? I'm known to ask for acronyms because you're gonna sit in lots of meetings once you graduate, and there will be lots of acronyms out there. So I want to make sure that you fully understand those acronyms, and you don't want to ask that question in the middle of the meeting. What does an ITS mean? I'm gonna feel bad myself. So please, if I ask what's ITS, you should be able to know. What are the two dimensions that we're working with in any transportation system? These are again, it's time and space. What are the three areas of involvement if you become a transportation engineer? Again, I'm expecting you to know it's planning, design, and operation and management. Give me 3 or 4 aspects of any geometric design problem. So if you are a geometric designer, give me your three or four components of that geometric design report that you're going to end up writing. So you have here again highway engineering. You have so highway engineering, grade, surface texture, side distance, horizontal and vertical alignments, as well as speed limit. And again, when I'm pausing on certain slide, that doesn't mean it's not important. But like for example, what's USDOT? I hope you know it by now. United States Department of Transportation. What is MPO? That's the Metropolitan Planning Organization. What is TxDOT? Again, if for the ones who are going to be transportation engineers, good chunk of you might be working at TxDOT. So it's Texas Department of Transportation. I'm not expecting you to know every single one of these because they are a lot, but FAA, Federal Aviation Administration, FHWA, Federal Highway Administration, FTA, Federal Transit Administration. So some of these again are more known than others. I can ask you, give me a couple examples of other federal agencies that deals with transportation role. So here you have again, Department of Homeland and Security, U.S. Forest Service, National Park Service, and Indian Affairs. AASHTO. What is AASHTO? This very known question. AASHTO, the American Association of State Highway and Transportation Officials. What's ACE? I hope you know it by now. This is the American Society of Civil Engineers. What's TRB? A big conference that happens in Washington, D.C. every January. And this year it was the 100th meeting, actually. Virtual this time for coronavirus sake. But TRB, Transportation Research Board. ITE or ITS, those are always, again, something needed. You need to know them and what do they really mean. I think I've talked about this before. As an engineer, you must consider what do you need to consider as a traffic engineer and as an engineer in general. Again, first thing safety, then economy, then quality of service, quality of life. So I can ask you again, give me the top two or the top three. You should be able to tell what are these. Oh, and of course, the fourth is the risk. I'm not gonna ask you again what's your expected salary. I hope again it's gonna be on the higher side of these numbers, but I don't think I'll ask that. So that's basically the first chapter. From the first chapter, again, you will be seeing couple conceptual questions. What's the difference between this and that, or define for me this, or what does that mean? Those type of questions. Because again, chapter one, as you could see, there's no calculations, but I'm going to ask you from chapter one some conceptual questions just to make sure that you grasp the concept of that chapter. Let's go on now on the next. Give me a second here. Oh, chapter one was still actually still not done with chapter one. There is lecture two for chapter one. Lecture two for chapter one. I'm loading it. Bear with me for a second. All right. Chapter two, lecture two. Again, some conceptual questions, very important ones. I can ask again. Let's for me some transportation modes. Or again, these are the major transportation issues. Give me three challenges out of six that transportation engineers will deal with in the next couple decades. Transportation modes, I can ask you to list them for me, or I can ask you again, what are the, give me two or three advantages of the trucking industry, or a couple advantages of the railroads, or a couple disadvantages of having to use pipelines. Those are the things, again, conceptual questions related to chapter one. So any of these, again, same thing will apply, advantages and disadvantages, but using your own words if you desire to do so. And again, the issues, really the issues, I can ask you again, give me two or three of these issues, or I can ask you to explain for me something like, what's the difference between demand and supply? Define the demand and define the supply. I can also ask you again, when it comes to environmental protection and environmental issues related to transportation engineering, what are the negative impacts that we can see? List for me three out of the six or the five that I mentioned. Again, noise, pollution, all the way to congestion. Again, ITS, I can ask you again, give me two or three technologies that uses intelligent transportation systems. So we've talked about the way in motion, we talked about the GPSs, we've talked about electronic fare payments or video imaging processing. All of these, again, we've discussed them in detail. Then we talked about the gas tax. I can ask you, what does it mean? Explain for me what's a donor versus donee states, and explain that to me. And I would hope that you are remembering again which is the most state that's getting way more than they are contributing, which is Alaska. And sad to say that the least state that gets um, money compared to what they contribute is our own very state, Texas. So that is again, that's the second lecture of chapter one. Any question?
So we're gonna meet in your your class in person next Thursday. Is it the same class that this class was scheduled to be at? Same classroom?
Say that again, please.
I said we're going to be taking this test in person, correct? Next Thursday,
Yes, yes.
and this is going to be in the same classroom that this class was initially scheduled for.
Yes, I will be going today to that room and checking again if we have enough. We are having here 27 of you, so we should be having 50 plus seats in that room. If not, I will communicate to all of you through Canvas if we are changing the location just to fit all of you and keeping the social distancing. But for now, yes, we're
Okay.
gonna keep it as what's mentioned on your Canvas or on your my YouTube title.
All right. Thank you.
Thank you. All right, so chapter 2. Let me share that. Okay, chapter 2. Uh, Again, you're going to see a couple of problems, either again, some calculations and some conceptual questions from chapter 2 when we talked about the attractive force and resistance. I can simply ask you, give me what are those three major forces that any vehicle has to fight, if you will, against to move forward. These are the aerodynamic, the rolling resistance, and the grade or gravitational resistance. That's why the first letters always are, that's the resistance. But then again, the A refers to the aerodynamic, RL rolling, or G, that's the gravitational resistance. So this equation, by the way, is one of the few equations you're not going to be given in the exam. I'm expecting you to know it. So it's the mass of the vehicle times the acceleration plus the three resistances. Again, aerodynamics, rolling resistance, and gravitational. But for each one of them, again, I'll provide the equation for each one of the resistances. But I can ask you also, give me the major source of the aerodynamic resistance, or give me the three sources. So it's again, you can name them, the three sources right here, or you can just mention the major source if I'm asking you for the major one, and that's the turbulent flow around the vehicle body itself. The equations again will be provided to you, so not to worry. But you need to make sure, again, this is important now for the exam as well as the homeworks, is what am I asking you for? Is it resistance, which is in pounds and or newtons, and if that's the case, you're going to use this equation, or am I asking you for a power, or am I asking you for horsepower? So the trick is not really to remember the um, the equation or to ask for the equation. I'm gonna give you all the equations, but the problem is again you need to distinguish which equation are going to use for what um, question. So again, here this is the resistance, this is the power, just the power, and which is again in feet pound per second, or the horsepower. And we've gone through multiple examples to differentiate between the three requirements. We've talked about the rolling resistance as well. I can ask you the same thing. Give me the primary sources of the rolling resistance in the field, or what are the major factors that affect the rolling resistance, whether to increase it or decrease it. And those are, again, the tire inflation, the temperature, and the speed. Again, very short answer. Lots of those little short answer questions. That's typically what I use. Again, the equations are going to be provided, but you need to make sure that you know how to use them right.
Will we also be given conversions, or we memorize those?
What kind of conversion are we talking about? The
I
speed,
mean,
for example?
obviously we did the ones in the horizontal curve of those, like the 1.467. But is there any other ones that we need to know?
Not that I'm aware of. No, really, the major conversion was in chapter 3, which again, you don't have to remember it, but you can do it again, 5280 over 3600 to convert from miles per hour to feet per second. Besides that, trying to remember if there is any other conversion that we had, but no, that's about it.
And
Again,
also, this document we're looking at is also a test review, correct?
yes,
This is posted.
the one that we're recording now.
Yes.
Yes,
Well, not the lecture, but there's the actual PowerPoint.
the actual PowerPoint. This is, yeah. All these PowerPoints are already posted. Those are the. I'm using the same PowerPoint that we've used before.
No, I was just saying there was a test review one, but I see you're just going through all the different ones. Okay, that's all I was asking if this was compiled or not, but it's all right.
Yeah.
Thank you.
Typically, again, maybe I have a different style compared to other instructors, but I just because you guys are familiar with the PowerPoint, I like to go through the PowerPoints themselves and just point out to what's important.
No, I agree with it all. I was just confused at first because it was when you're cutting in between, but we're all good. I just was curious, but yeah, I agree with that.
Thank you. And then the third resistance is the grade resistance. Again, we've gone through the derivation. I don't think I'm going to have the leisure in the exam to test you on how to derive the equation, rather than, again, just concentrating on the usage of the end result of that equation. And we've gone through, again, please make sure that you resolve the examples that we've gone through in the homework, as well as during the class. Those are more than what you need for the exam. Then we've gone through the practical stopping side distance. Again, this is the basic physics equation, but really what we ended up using is this is the first equation. This is, again, the practical stopping distance. And then we've talked about, again, this equation will be provided. You're gonna make sure, again, that the V here, again, is in feet per second, not in miles per hour, because the A, which again, I'll be providing that if we have a question like this in the exam, is feet per second squared. Or if everything is in meters and seconds, it's going to be 3.4. So if you put that as 11.2 feet per second and the velocity is 50 miles per hour, again, the results are erroneous. Here, again, I can ask you, what are the steps between perception to reaction? So perceive, comprehend, respond, and react. Those are the steps. And then we got to know it's not just about the distance you're driving once you push on the brakes. It's actually, there's another distance between perceiving and reacting. And that's why this is the DR, your original speed times TR. TR, I'm expecting you to know that number, 2.5 seconds. This is AASHTO standards, a very conservative number. If it's not given to you in the exam, you always have to use 2.5 seconds. And I'm expecting you to remember that number. We've gone through a little example here to show you, again, the what does, again, DR mean. Just even if it's just 1.5 seconds, you'll be driving 132 feet before you push on the brakes. And then, of course, the summation of the equation, ds is equal to the total stopping distance, which is the dr plus the d. The dr, this is distance traveled during perception reaction time, plus the distance now traveled during braking. Once you push on the brake, you're not going to stop right away. You're going to be driving some distance, and that's the d. So this d is, again, the v squared over the previous equation, which is right here, v1 squared over 2g times a over g plus or minus g, while the dr, this is the original speed, v1 squared times tr, which is typically 2.5 seconds, unless if it's mentioned otherwise. I can ask you also, what are the driver characteristics and conditions that can contribute to increasing their reaction time? So I can ask you, give me 3 or 4 of those 6 of them. So age, medical condition, alcohol use, fatigue, sleep deprivation, all the way to the emotional condition. And then we talked about the dilemma zone. Dilemma zone, again, we can do a simple calculation. We've gone through those. Again, the equations are going to be provided to you. And then I may give you the example, and then I'll ask you again, are we having a dilemma zone at this location or not? I'll provide you with the yellow time, for example, what was the speed, what's W, what's L, and then you need to compare and see. Again, if XC versus the X node, and we've gone through again the three different cases where again this is the okay zone. This is an optional zone where X node is equal to XC. But now once XC is more than X node, the difference between the two, this is the distance now where if the car is at this location, it will be at the dilemma zone. Because if it's right here, if the X node is far away from XC, then you're gonna stop. If you are here, you're gonna speed up and clear the intersection. But if you are within this distance, this is what we call the dilemma zone, where again problems begin. Or I can ask you, what's the minimum yellow time that you can design for this signal to reduce or even eliminate the dilemma zone? So we've gone through this equation right here to do that. At least this equation is gonna satisfy this situation. At least xt is gonna be equal to x node where there's no dilemma zone. How can you do this? I can ask you a simple question. How can you improve the or remove the dilemma zone? Either by changing the speed limit, that is number one, or selecting an appropriate minimum duration of the yellow signal phase, and that is number two. So either of the two will make the dilemma zone almost diminish. So that was chapter 2. Any questions on chapter 2? Again, from chapter 2, you will be seeing at least a question or two calculation questions and a couple questions conceptual as well. All right, and then it was last chapter, which
Hey,
is
Professor, just to clarify on chapter 2, all the equations are given except the F equals MA plus the resistances. That's the only one we have to know.
let's see here, chapter 2
Yeah, sorry. It's on page 4.
or
I
slide 4,
I I wasn't sure if you said we had to know it or if it was given.
slide 4,
Yes.
slide 4. Slide 4, the F is equal to MA plus RA plus RRL plus RG.
Mhm.
Yeah, no, this you have to know.
Okay. Cool.
This you have
Thank
to know,
you. Just clarify.
of course. Because yeah, the bottom line really again, if it's a conceptual equation that is not long and it's just again really that you need to know that there are three different resistances plus the mass of the vehicle times the acceleration. This is the conceptual question, conceptual equation. Besides that, again, I'm not expecting you to know rho over 2 times CD times A times B squared. That is
Okay. Awesome. Also, there's someone in the chat who asked if we can use the FE packet for the exam.
No, the answer is no. The reason why, if you really go through the FE packet, and if you don't want me to provide you the equations, I'm fine with that. But you're gonna take 2 to 3 times the time to find the equation. Trust me. The exam will be a couple pages, and then at the end of the exam, there's 3 or 4 pages equations. They are tailored towards chapter 1, 2, and 3. I've done it. I've done this class for 7 years, and for the first couple of years, I used the FEA packets, and the students they find it. So, and this Susan is that now we provide it to you. Book, think there should be some. Let me see here. I'm opening the textbook. Let's see here. Chapter 2. I don't think so. No. So if that's the case, again, you just use the example that we've gone through on the PowerPoint. I think I don't know if that section maybe is not there, but I had to add it because it's an important section, and I've seen it being utilized and asked about in multiple occasions. But Jose, again, basically, if you just understand the problem that we've gone through in the PowerPoint, that's more than enough for the exam. Any other questions? All right. chapter 3. Chapter 3, again, this is the most fresh one on your memories, I hope. And it is, we had lectures 5, 6, and 7 on that. So let me share the screen again. All right. So it's all about vertical and horizontal alignment. At the beginning, though, we've gone through some theoretical part that I can also ask you about. So give me the basic elements of any highway geometric design. You should be able to tell this: the cross section, the horizontal alignment, super elevation, vertical alignment, any channelization at grade, of course, and roundabouts and traffic calming devices. What are, again, determine this the specific. Let me see. I have something on the chat. The limit zone is explained in chapter 7, page 250 in the book. Good. Okay. So Susan is saying dilemma zone, Jose and others is on chapter 7, page 250. Good catch. For some reason, again, I like to put it on the chapter for chapter 2 because it's related to the side distance, but the author has different opinion. All right. What else? Yeah. Again, the H2. What does H2 really mean? Simple question, but what are the cross-section elements here of any roadway? So we can say again, it's the pavement, the lane width, the shoulder, the curb, all the way to right of way. What I can show you a picture like this, and the picture again will explain. I can show a picture just empty, and then I can ask you, what is this? What's this? What's that? So you need to know, if I show you a cross section, you should be able to name those little components: the pavement in the middle, then the shoulder, then the clear zone, then all the way to the additional right of way from the two sides. Pencil pictures, lots of pictures, and then we arrived at the vertical alignment. Vertical alignment, I'm expecting you to know where is the PVC, the PVI, the PVT. I'm not going to draw that for you. I'm just going to explain, okay, the beginning of the curve, or the PVI station is this, or the PVT station is that. And then you should be able to do like what we used to do in statics, free body diagram. Same thing, more or less here, where you're going to draw the problem. So it's going to make it much easier and much more visualized to you before you start crunching the numbers. So you need to understand again if it's a crest or sag vertical curve, because really this is very crucial, because we got to know horizontal alignment, it's one set of equations. But for vertical alignment, it really depends on whether it's a crest vertical curve or a sag vertical curve. So please be aware that, again, the equations are different, and you want to make sure at the very beginning to understand and define for you whether this is a crest vertical curve or a sag vertical curve. Not every time I'm going to define that for you. You're going to be able to define it by, again, positive G after a negative G. That's a clear vertical curve. Or, again, steep G1 and then less steep positive G2. That's also a crisp vertical curve. Look up, again, the lecture that we talked about vertical curves to explain for you how can you differentiate. Looking at G1 and G2, how can you differentiate between crisp vertical curve and sag vertical curve? Okay, so another equation that I'm expecting you to know, conceptual equation. This is A. A here, this is absolute value of the difference in grades. So it's that's G2 minus G1. This is conceptual equation. If I know it, which I remember it, I should be expecting you to remember. So that's G2 minus G1. You are not going to be provided that in the exam. This is now we've gone now through the parabolic equation. This is also, again, I did not teach you new stuff here. This equation was parabolic equation. I'm expecting you to know that y is equal to ax squared plus bx plus c. Simple and straightforward. Also, I'm expecting you to know those three numbers. Sorry guys, but yes, you need to know these. So the a here, the small a, is G2 minus G1 over 2L. And the B is G1, and the C, this is the elevation of the PVC. How can you get the C? Again, if you put the X equal to 0, you're going to get the C is equal to the Y, the elevation of the beginning of the curve, PVC. So this is an important slide here, slide 21, for you to understand and memorize the equation. Again, everyone knows that since high school, I hope. Y is equal to x squared plus bx plus c. But what you need to know extra, again, the A is here G2 minus G1 over 2L, and the B is G1, and the C is the elevation of the PVC. But of course, when it comes to the offsets, all these equations are going to be provided to you. How can you get the offsets, the maximum? Now the offset at the midpoint, the offset at the final or at the end of the curve, those will be provided to you. But of course, you need to know what's A, which is again G2 minus G1, the absolute value of that. K, this is another conceptual equation. K is equal to L over A. That's again L over A. That's as simple as that. The length of the curve over the change in the grade. So L over A, that's an equation I'm expecting you also to know. XHL, again, this is going to be provided to you if you need to. And of course, the problems that we've gone through, very important to know how to run these problems and how are they solved. And then the SSD. So this is here now again. You see now the differentiation between the crest vertical curve and the sag vertical curve. So this equation is the general equation that we've introduced in the previous chapter. This equation will be provided to you. Although again, it's one of the conceptual ones, but this one I typically provide. But the T, I'm expecting you to know. Again, T is 2.5 seconds. Unless if it's something else mentioned. Again, if I tell you that the T is 1.5, we're going to use 1.5 seconds. But if nothing is told about the T, the TR, you're going to use 2.5 seconds. You need to make sure you're using the right table. I'm going to give you multiple tables. But table 3.1, this is the stopping side distance for crest vertical curves. This is the general one for everything. But now from here, yeah, I'll take that back. So the 3.1 to give you the side distance in general. But from here, you see now the side distance and the crest vertical design. So we've gone through the equations, H1 and H2, the height of the driver and the height of the roadway obstruction. And then those equations are going to be provided to you. But I'll give you, guess what? I'll be giving you these equations as well as these, as well as the others. So you need to make sure which equation you're going to need to use. So you really need here to not remember the equation, but at least have an understanding that, okay, so H1 and H2, this is again for S less than L. That's the equation that I want to use first. And if I satisfy the assumption, this is the SSD, the stopping side distance, then I'm good. If I do not satisfy the equation, then I need to go to the second equation and use that equation. So this is here. When should you use this equation? If I give you a specific H1 and H2. If I did not talk about what was the height of the driver or what was the height of the obstruction, then you're gonna, by force, if you think about it, you're gonna be using these equations. Because please do not stop at the exam and ask me what's H1 and what's H2. If I did not provide you what's H1 and H2, then you would know by default that now we're using the default values from the AASHTO. H1 is that much, H2 is that much. I'm not expecting you to know them, but basically I'm saying if the H1 and H2 are not provided, then you're gonna by default you're gonna use these equations: A times SSD squared over 2150, or the other equation if the SSD is higher than the L. Or the third simplification again was the K value. Again, if you know the K, again, K is equal to L over A. Again, if you know the K from the table, you can multiply that by A to get the L value. But you need to make sure again this is table 3.2, design control for crest vertical curve based on the SST. This is how to get the design K and from the equation. The equation is not going to be here. I'm not going to be again that crafty to remove the little note at the end. I'll keep it, but you need to make sure again you're reading the instruction and the K is equal to L over A right here. Then we've moved now to the SSD and the SAG vertical curve. So they are two different sets of equations. So the SAG vertical curve, it was heavily dependent on the beta and the H, the height of the head beam and the angle from the horizon. So again, if I'm providing you the h and the beta, you're going to use these equations. And of course, these equations are going to be provided to you. If there's no information about h and beta, you're by default, you're going to use these sets of equations instead. And again, this is table 3.3, design controls for sag vertical curve. Please make the distinction between 3.2 and 3.3. 3.2 for crest vertical curve, 3.3 for sag vertical curve. The K values are going to be different. The equation is the same, but the values are different from sag to vertical curve, from sag to crest vertical curve. This slide, again, I'm not testing you about. This is, again, self-study, so it's not going to be included in the exam. And then we've studied another interesting situation, the underpass side distance. So we were very interested in that HT, the clearance. So H1 and H2, and then the clearance, HC. We've gone through the derivations. Again, we have, this is the HT, what we're after. Again, if I'm giving you H1 and H2, you have to use these equations because this is specific situation. If I'm not talking about H1 and H2, you're going to use these equation sets instead. Once you do those, you need to compare it like what we've done in the very last example for the vertical alignment. You need to compare the HT that you're getting from any equation to the minimum. Remember, we did an HT and it was like 8.5 feet. And if it's less than the minimum, so that 8.5 feet, you're going to cross it and you're going to use the minimum standard set by AASHTO. That's 14.5 feet. But if you do the calculation and the HC is equal to, let's say, 16 feet, you stick to it. You don't downgrade. You always have to meet the minimum spec. But if your calculation is way higher than the minimum, you stick to that number. Always pick the higher. Always pick the higher. So from this half of the chapter, you're going to see again and a question or two calculation questions, as well as maybe a question or two also as conceptual questions. The last lecture related to chapter 3. Can you see this? Can you see lecture 7 here, or do I need to stop the share and share again?
No, you need to share it again. We can't see it.
All right, I figured. Chapter 7 or lecture 7. Okay, so lecture 7 was about the the horizontal alignment. We defined it, and then we've gone through the derivation. As I said, derivation, it's not the time to check your knowledge on how to derive the equation in an exam, but really the equation, this equation right here, I'll be providing this to you as well. Don't worry. Although again, it's a conceptual one, it came from a derivation, but I'll be providing that to you. What's the radius, the minimum radius of the curve? But I can ask you, what are the factors that affect the radius of the curve? You need to list those for me. So the super elevation, that's 1. The speed design, that is 2. And then the maximum side friction, that is 3. So those are the 3 factors that affects the selection of the minimum radius of the curve. And then table 3.5, familiarize yourself with that table. If I ask you, just go ahead and use a table and get me the radius. Again, this will be, this is going to be your source. So this is the speed limit. This is the super elevation. And this is the calculated RV. And this is the rounded RV. I can ask you, please list for me what are the 3 or 4 other different types of horizontal alignments. So there is the simple curve, there is a reverse curve, there is a compound curve, and there is a spiral curve. And then again, we defined same thing here when I give you a question. And again, I'll be blunt here. You will have questions, at least a question from the horizontal alignment and a calculation question from the horizontal alignment, and one at least from the vertical alignment. So you're gonna see it again. There's no really surprises here. So you need to familiarize yourself also with this schematic here. I'm not going to give you that. I'm going to give you information. I'll tell you what's the tangent or what's the alpha. I mean, what's the delta or what's the M or what's the E. But you need to familiarize yourself. How can you draw the information given to you in an exam so you can solve of what's needed to be solved for. But I'll give you all these equations. I'm not going to define what's T for you or what's T, but you need to understand that. But all these equations from D to T to M, E, and L will be provided to you. And again, please, please, please make sure that the delta is in degrees. In the screen of any of the calculator that you're using, there is a little D. Please make sure there is no R, that's in radian. Make sure it's in degrees. Otherwise, the numbers are going to be funny ones. And then the last one was the stopping side distance, which is again the middle, the MS distance right here, the middle ordinate. So these are the two equations that I'll be providing to you. So I can ask you what's the available side distance, given the fact that MS is that much, or I can tell you we have certain MS based on having a tree or a billboard. What is now the available side distance for this location? So one of these two equations might be used if I'm giving you an example related to the reduced MS because of site obstruction. Any question on this part? Again, you will be given at least one calculation question from this half of the chapter, as well as maybe one or two simple conceptual questions. Questions? I hope this was helpful to give an idea what to expect in the exam. Again, nothing really. If you follow the PowerPoints, as well as if you did by yourself your homework, you should be more than prepared for the exam. It's 10:45. I think if there is no question, and let me check the chat box. There's nothing in the chat box. Again, thanks for your attendance. 22 of you here, so 5 didn't make it. But again, I'm recording this lecture and I'll be posting it either today or tomorrow at the most, so you can go back and see it again. Questions? All right. Thank you so
Thank you
much.
very much.
Thank
Thank
you
you.
all. And again, I'll be communicating with you for the exam. The exam will be on Thursday, and we'll keep you posted about that. Thank you.
Thank you,
Good one.
Professor.
Thank you, Professor.
Bye-bye.
Bye.
Thanks.